Welcome to our presentation, CPF, Learning a Contact Potential Field to Model the Hand-Object Interaction. The presenter's name is Lixin Yang from Shanghai Jiao Tong University. Modeling the interaction of hand and object has been studied for a long time. Conjoint hand-object pose estimation usually not paid full attention on the contact between the surfaces of hand and object. However, contact can provide rich cues to guide an accurate pose or natural grasp estimation. In this paper, we present a hybrid learning fitting solution that integrates the contact modeling into the current hand-object pose estimation pipeline. First, to represent the interaction, we define that the contact between a hand and object mesh surface is a multi-point contact, which involves multiple hand-object vertex pair affinities. These affinities are regarded as contact semantics that depict the pairing of a hand part and object vertex that come into contact. Intuitively speaking, with this representation, we want the interaction behavior to pull the affinitive vertices close. While the noisy prediction occurs, for example, the model penetration, we also want the repulsion behavior to push the penetrated vertex away. Then, to model the attraction and the repulsion behavior, we treat each contacting hand and object vertex as a spring mesh system. The two endpoints of the spring is a counterpart of a pair of hand and object vertex. The spring's rest position depicts the situation that those two vertices are in perfect contact. The spring's elastic property is another counterpart of the contact likelihood of those two vertices. With this definition, we can model the hand-object interaction within an elastic potential field, as we call the contact potential field, CPF, which is determined by the minimal elastic energy at the ground truth grasp position. Representing the contact in the CPF has two advantages. CPF is able to assign per vertex contact semantics to the object mesh. As illustrated, the contact semantics is the contact point on the different hand parts. By minimizing the elastic potential energy, CPF can uniformly avoid interpenetration and control the disjointedness. To integrate the CPF into image-based hand-object pose estimation, we present a hybrid learning fitting architecture for modeling the interaction of the hand and object, as we call it MIHO. MIHO consists of three stages. The first HONET is a common ResNet regression module that predicts the hand pose and shape parameters in manual representation and the object 60 pose. The initial prediction in HONET doesn't consider any constraints, hence it suffers from severe interpenetration or disjointedness. The second stage is a pixel-wise contact recovery module, Picker. Given the raw image and the predicted object pose in HONET, Picker first adopts a feature extractor that converts the raw image into the contact feature map. Then we project the object vertices from its initial 3D position into the feature map. Next, we gather the pixel-wise feature points and convert them into the point-wise feature points through a point-net encoder. Finally, three cascaded multi-layer perceptrons yield three outcomes. The first vertex contact, VC, decides which vertices on object surface are in contact with hand. The second contact region, CR, decides which hand part is most likely to contact with those vertices. With VC and CR, we can construct the attractive spring mesh system to form the CPF. The third anchor elasticity represents the likelihood of the predicted contact pairs. The final stage is a grasping energy optimizer, GEO, that refines the initial hand and object poses. The loss function of GEO consists of three terms. The first is the elastic energy that brought from the spring in CPF. The second is the anatomical loss that maintains a valid hand pose during fitting. The third term is a regularization term. The elastic energy brought from the attractive spring mesh system is given by the Hooke's law. Besides, we also introduce the repulsive spring that pushes the hand if its vertex is in the vicinity of the object surface. Hence, the elastic energy in CPF is the sum of the energy stored in all the attractive and repulsive springs. The original manual pose representation consists of 9 degrees of freedom for each finger's rotations. The GEO suffers from severe hand pose abnormality during fitting. Thus, we extend the original manual coordinate system to the anatomical aligned system, in which we depict the rotation with respect to the twist, bend, and splay axis. Therefore, we add the anatomical loss in the GEO's energy function to mitigate the hand abnormality pose. We call this hand model A-manual. We benchmark the MIHO's performance on two different datasets. MIHO brings significant improvement in terms of the physical related metrics. As the penetration depth, solid intersection volume, disjointed distance, while only suffers from minor performance cost in the mean vertex error. As illustrated in the qualitative result, MIHO is able to repulse the intersection away and attract the disjointedness to touch. The pose estimation from MIHO is sometimes superior than the ground truth annotation. This video shows the geo's fitting process. The initial pose value is predicted from the first stage, WholeNet, a pure learning-based model. Our code and model are available. Welcome to our poster for more technical details.